I have a real love-hate relationship with the whole concept of hydrogen bonding. Hey there, OChemNinjas. Intermolecular forces are a concept that's always kind of lurking in the background of chemistry. You probably talked about it in high school chemistry, you probably talked about it in general chemistry, and we're going to talk about it again here in organic chemistry. This video will look at the intermolecular forces from an organic chemistry perspective. Intermolecular forces you could think of as the stickiness between molecules. How well do molecules stick to themselves or others? Intermolecular forces contribute to properties such as the melting point and the boiling point. So thinking of intermolecular forces as that stickiness between molecules is a good analogy. If the various molecules in a solid are stuck together through intermolecular forces and I want to turn it into a liquid, I want to melt it, I'm going to have to input energy into the system in order to unstick them and allow them to flow past each other in a liquid. How much energy I need to input, how high the melting point is going to depend on how sticky those molecules are toward themselves. If the intermolecular forces are very strong, it's going to be really hard to unstick those molecules. I'm going to have to put in a lot of heat energy to unstick those molecules, and the melting point is going to be very high. If the intermolecular forces between two molecules are not very strong, then they're not going to be stuck together very strongly, and it's not going to require much heat energy to split them apart to allow them to be a liquid. Such a molecule would have a very low melting point. The same is true if I take those liquid molecules and I want to make them into a gas. If I want to boil the molecule, I'm also going to have to input energy. How much energy depends on how sticky those molecules are towards themselves and others, and how much energy it's going to take to allow them to escape into a gas. In general, the stronger the intermolecular forces, the more sticky the molecule is to itself, and it's going to require more energy to do a phase change. Intermolecular forces also impact solubility. The more similarities there are in the intermolecular forces between the solute and the solvent, the more they can stick together and the more the solute can be soluble in that solvent. If the molecules are very dissimilar, there's not a lot of interaction that can take place, and so it's hard to dissolve that type of solute and that type of solvent. There are three main types of intermolecular forces that are important in organic chemistry. Let's go over them now. The first interaction we're going to talk about is not really an intermolecular force. Ionic interactions are electrostatic interactions that hold together salts in a crystal structure, like the sodium chloride crystal structure. It's a very strong force. Salts can have melting points in the thousands of degrees Celsius, but it's most technically not an intermolecular force. Intermolecular forces are the forces between two different molecules that stick them together. Ionic bonding is an intramolecular force. Within the NaCl structure, it's the electrostatic interaction between the sodium and chloride molecule that holds that salt together. A lot of times, ionic interactions are grouped in with intermolecular forces, but technically they're not intermolecular forces. The first intermolecular force that we're going to talk about is London dispersion forces. London dispersion forces work on the concept of an induced dipole. What is an induced dipole? Every molecule has a cloud of electrons surrounding it, and you can think of that cloud of electrons almost like holding like a baking pan of water. If you were to try to walk around with a baking pan of water, all the water would slosh over to one side and then would all slosh back to the other side, and this water would be sloshing back and forth, and there'd be a buildup of water on one side, and then it would build up on the other side. The same is true with the electron cloud. The induced dipole is similar. As these molecules are tumbling around in the flask, that electron cloud is sloshing back and forth. Sometimes the electrons build up on this side, sometimes they slosh over to this side. And if the electron density sloshes over to this side of the molecule, it induces a partial negative charge on that side of the molecule. We use the Greek lowercase delta to indicate the partial charge in a molecule. This side of the molecule doesn't have a full negative charge, it just has excess electron density, giving it a partially negative charge at this point in time. And if most of the electron density is sloshed over to this side of the molecule, that means there's a lack of electron density on the left side of the molecule, and so the left side has an induced partial positive charge. And if the right side of this molecule is partially negative, that will repel the electrons away from the left side of the neighboring molecule, giving the left side of the neighboring molecule a partial positive charge. It'll push all the electrons over to the right side, giving the right side an induced partial negative charge. And this continues around the entire structure. The partial negative will induce a partial positive in the neighboring, pushing all the electrons down to the bottom, which will induce a partial positive over here, partial negative over here, partial positive over here, partial negative over here. And throughout the whole structure and throughout the whole network of molecules, we get these induced dipoles. The problem is these induced dipoles are very transient. They just don't last very long. Just like when you're walking around with a tray of water, it'll slosh to one side, but it won't stay there very long. It'll immediately slosh back over to the other side. So as soon as all these induced dipoles form, the electrons slosh somewhere else, and we get a new induced set of dipoles. And that keeps happening over and over. The dipoles form, the electrons slosh, we get new dipoles, they slosh again, and it just happens over and over again. As a result, the London dispersion forces are the weakest intermolecular force. If the only thing a molecule has going for it is London dispersion forces, then the molecule's not going to be stuck together very tightly, and it would not have a very high melting point or boiling point. Good news, every organic molecule in the universe has London dispersion forces. Bad news, they're very weak. One more thing before we move on to the next topic. When I talk about adding energy to break the molecules apart to do a phase phase change, I don't mean breaking the covalent bonds within the molecule. Covalent bonds are exceedingly stable. It would require a lot of energy to break a covalent bond. No, what we're talking about is intermolecular forces. When we add energy, we unstick the molecules from each other. We unstick this molecule from the rest of the chain and move it off as a gas. We unstick this molecule from the rest of the liquid and move it off as a gas. We're separating the molecules, breaking the stickiness between the molecules with these intermolecular forces. The next intermolecular force is dipole-dipole interaction. Dipole-dipole interactions occur when a molecule has a permanent dipole. That is, when there's a polar bond between two atoms of different electronegativities, giving one side of that bond a permanent partial negative charge and the other side of that bond a permanent partial positive charge. With the permanent dipole, the partial negative of one side is going to be attracted like a magnet to the partial positive of the next molecule. And that molecule's partial negative will be attracted like a magnet to the next molecule's partial positive. And so on and so on and so on. And all of these molecules can stick to each other through these dipole-dipole interactions. Because the dipoles for an individual molecule are permanent, the stickiness between these two molecules is going to be a stronger force than the induced dipole of the London dispersion force. This increased intermolecular force, this increased stickiness is going to mean that these types of molecules are going to have a higher melting and a higher boiling point. To be clear, the interaction between any two molecules is still transient. Once all these molecules line up with their dipoles in line, they're going to break apart and they're going to move over and interact with other molecules and to form a new lattice of dipole-dipole interactions. It's still transient, but it's stronger than the London dispersion forces. The last intermolecular force we're going to talk about is hydrogen bonding. And I got to tell you, I have a real love-hate relationship with the whole concept of hydrogen bonding. First off, even though we say bonding right there in a name, hydrogen bonding is not a real bond. It can't be. It's an intermolecular force. It's a stickiness between molecules. It's an interaction between two different molecules. It's not a covalent bond holding a molecule together. The hydrogen bond is an intermolecular force between a heteroatom with a lone pair, that heteroatom is nitrogen, oxygen, or fluorine, and it interacts with a partial positive charge of a heteroatom-bound hydrogen on a neighboring molecule. The polar HZ bond gives the hydrogen a partial positive charge, making it lack electron density. The lone pair of electron has excess electron density, so it shares some of its electron density with the partial positive charge on the neighboring hydrogen, stabilizing the whole system. And that leads me to my second pet peeve about the concept of hydrogen bonding. This heteroatom has the electron density, and it's using it to share its electron density with the hydrogen. Negatives attack positives. It's the whole thing we've been talking about in this whole course. But do we call this heteroatom lone pair the hydrogen bond donor? No. We call it the H-bond acceptor. It's not accepting anything. It's donating its lone pair of electrons toward that hydrogen. Instead, we call this hydrogen the H-bond donor. It's just completely backwards from the way we think about electron flow in organic chemistry. But this is the convention, so you will have to accept these terms. We think about hydrogen bonding most in a molecule like water. The lone pair on oxygen can share some of its electron density with a neighboring hydrogen on a neighboring water molecule. The neighboring hydrogen has another oxygen attached that can share its electron density with another neighboring hydrogen, and we get this whole network of hydrogen bonding throughout the entire network of water molecules. But hydrogen bonds are also transient. Once this network forms, the water molecules will move away from each other, they'll break those hydrogen bonding interactions, and they'll form new hydrogen bonding interactions with new water molecules. Hydrogen bond, though, is the strongest of the intermolecular forces we've seen so far. If a molecule can engage in hydrogen bonding with another molecule of itself, that's going to really increase the melting point and boiling point for that molecule. Let's put this in practice with a quick worked example. If we look at the molecules pentane, butyraldehyde, and butanol, they all have essentially the same shape, essentially the same molecular formula, essentially the same molecular mass. The only real difference in these molecules is the types of intermolecular forces holding two of those molecules together. If we look at pentane, it doesn't have any polar bonds, it doesn't have any hydrogens capable of hydrogen bonding. The only intermolecular force available to pentane is London dispersion forces. Every organic molecule in the world is stuck together through London dispersion forces. Butyraldehyde also has van der Waals forces available to it. Every organic molecule in the universe does. But it also has this polar carbon-oxygen bond, so it also has dipole-dipole interactions. It does have this hydrogen over here, but this hydrogen is attached to carbon. This hydrogen is not capable of hydrogen bonding. There are no hydrogens in this molecule capable of hydrogen bonding. And finally, for butanol, every organic molecule in the universe has London dispersion forces sticking it together. It also has a polar carbon-oxygen bond, so it also has dipole-dipole interactions. But it also has this hydrogen capable of hydrogen bonding. It's a hydrogen attached to the oxygen, so it is also capable of hydrogen bonding. We would expect the various molecules of butanol to be stickiest towards each other and have the highest melting and boiling point. So let's look at these trends. For pentane, the melting point of pentane is negative 130 degrees Celsius. With the stronger intermolecular forces available to butyraldehyde, those molecules are more stuck together and will require more energy to melt the molecule, so the melting point of butyraldehyde increases to negative 96 degrees Celsius. Butanol has London dispersion forces, dipole-dipole interactions, and is capable of hydrogen bonding, so it will have the highest melting point of all at negative 90 degrees Celsius. The same thing is true with the boiling points. Pentane only has London dispersion forces available. The boiling point of pentane is around 36 degrees Celsius. It's a liquid at room temperature, but just barely. The stronger intermolecular forces available to butyraldehyde is going to increase the boiling point relative to pentane. The boiling point of butyraldehyde is 76 degrees Celsius. And finally, the molecules of butanol are the most stuck together with their hydrogen bonding interactions, and so they have the highest boiling point at 118 degrees Celsius. I want to leave us with this molecule, neopentane. It's an isomer of pentane. It has the same molecular formula. how do you think its melting point and boiling point will differ from pentane? The only difference between pentane and neopentane is the shape. Pentane is a long straight chain that floats around like cooked spaghetti, and neopentane is very compact, almost more like a sphere. For the melting point, what matters when they change the shape is how those crystals pack together. For a long straight chain like pentane that floats around like cooked spaghetti, it's hard to get all of those molecules to line up in straight lines because they're all kind of tangled within each other. The more tangled the molecule gets, the less effective those intermolecular forces are. But with the spherical-like shape of neopentane, we can kind of stack those spheres together in a very nice regular ordered rigid crystal pattern. And because the spherical shape of neopentane packs so much better, it's going to be more sticky, the intermolecular forces are going to work better, and we're going to have a higher melting point than we would for a straight chain molecule. The melting point rises from -130 for straight chain pentane to -16.5 degrees Celsius for neopentane. That extra packing gives it extra intermolecular forces that makes it more sticky and harder to unstick, and so we need more energy to melt neopentane. With boiling point, though, it's different. The molecule is not in a crystal structure, it's free-flowing in a liquid. The shape isn't so important as the polarizability. Polarizability is how big our pan of water is. We have a very big pan of water, like a long straight chain. We can really slosh those electrons to one side or the other. We can really build up that partial charge. With a shorter pan of water, we can't really slosh very far, and so we don't get very strong partial charges for a shorter chain molecule. The increased polarizability of the straight chain pentane is going to make it harder to unstick those pentane molecules to turn it into a gas, and so straight chain pentane is going to have the higher boiling point. The boiling point for neopentane is 9.5 degrees Celsius. As we change the shape of the molecule, the effect on the melting point and boiling point diverge. Making the molecule more spherical and easier to pack raises the melting point, but making the molecule more compact makes the intermolecular forces weaker and decreases the boiling point. Now you are an intermolecular force ninja.
Thanks for joining us today, ninjas. Be sure to watch these other videos to level up your ninja training even more. As always, don't forget to like and subscribe.